Welcome to the garden. Because it's starting to get cold in the UK, or the temperature's dropped, certainly it's not getting cold, we're going to have a quick look at heat pump water heaters, because as someone that works in the industry, or refrigeration anyway, people ask me about these all the time at this time of year. So, let's start out with UK electricity, gas prices, kilowatt hour. That'll do, like for like. Do we trust these people? Off-gem. Price cap. I mean, you know what, let's just use that. So we'll ignore standing charge. Although if you're only using gas for your heating, i.e. you've got an electric cooker or something, you could do away with the whole 31.66 standing charge if you did go to a heat pump water heater that uses electricity only. So it might not be all bad, maybe. So we've got 24.5 electricity, 6.24 for gas. And when it says kilowatt hours, I'm assuming that is actually a kilowatt hour of gas rather than a unit of gas or a cubic meter of gas, which is what your gas meter probably reads. So 6.24, 24.5. 6.24, 24.5. So that gives us a minimum heat pump COP that you need of 4 for it to be economically viable for you to get a heat pump in terms of literally just the energy that you put in to heat your house. Now, one thing to remember that your gas efficiency is not 100%, so for every kilowatt hour of gas you put in, you don't get 1 kilowatt hour out of heating. And as far as I'm aware, even the most efficient gas combi boilers, are they condenser boilers? Most efficient gas boilers are about 0.94. So I'll put that in. Which means that for every 1 kilowatt hour of gas that you actually put in and you pay for, you get 0.94 kilowatts of heat out. So correct that to the COP on the heat pump, because obviously with your heat pump, every kilowatt hour you put in, if you've got a COP of 4, then you end up with 4 kilowatt hours or 4 kilowatts of heat. 1 kilowatt in, 4 kilowatts out, which gives you a COP 4. So when you correct it like that, we actually only need 3.69. And if you look on, there's that website that if you're into heat pumps, you've seen it. And they have a league table of people's heat pump water heater installs. And 3.7 to me sounds very, very manageable. Even in winter you could do that. The rating point is at 7 degrees ambient. And most of the ones that I've tested have been 4 and above, so it sounds easily doable for us. So what we'll do is we'll have a quick look at the sort of questions people ask about heat pumps, or the 4 common ones that I always get. Do I need bigger radiators with a heat pump? Maybe. I haven't seen your radiators, so I don't know. But general equation of heat transfer Q, heat, is equal to H bar overall heat transfer coefficient times area of the emitter times delta T, which is the temperature difference between the emitter and the medium that it's in. The emitter in this case is your radiator, and the medium it's in is your room. So what you have here is, this is heat watt. This is some sort of constant which is specific to your radiator, emitter, heat exchanger, whatever it is that you're considering, but it's a constant that's specific to it. I don't know if you heard that, but I just received about 1 million. I just had like 1 million notifications. That was rough. Start this again. Do you need bigger radiators for your heat pump water heater? I don't know, because I haven't seen your radiators or your underfloor heating or whatever it is. I've not seen yours, no idea. But the general theory behind this is that heat transfer Q, or heat input, which is into your room at this point, positive sign is into your room, is equal to H bar, which is the overall heat transfer coefficient in some circles you might know it as U, or 1 over R. If you're in construction, you know an R value, it's 1 over R. A, which is the surface area, times delta T, which is the temperature difference between whatever the heat emitter is, which is a radiator or some sort of heat exchanger in any of their forms. And the medium it's in is the air in your room. And what you find is that you can basically just ignore H because it's just a scale constant, if you will. And then what you've got is that the heat is proportional to A delta T. And when you've got a boiler, you're going to be circulating water at around 60, 70 degrees C. And your room is going to be about 20 degrees C. Again, this depends, but it's ballpark figure. So with a boiler, delta T is approximately equal to 50 K, we'll say, which is 70 degrees circulation temperature, 20 degrees room temperature, so you've got 50 K to do it. If you've got a heat pump water heater, and if you're in winter, it's probably going to be about 50 degrees C that you circulate, so your delta T is going to be equal to around 30 K. And if you're in summer when it's a little bit warmer, I suppose I should write winter, and then summer heat pump water heater, your delta T is going to be about 15 because they'll circulate water at about 35 through your radiator, so you're at 15 K. So what you find here is because this delta T is smaller, you have to make A bigger just to make up for the same amount of heat input. So depending on how big your radiators are, yes, you might need bigger radiators, and this is the reason for it. But it's very much installation dependent. I haven't seen your radiators, I haven't seen your underfloor heating, I haven't seen your flow rates, because that's the other thing you can do is you can put flow rates up. It depends on the installation, and this is sort of one of the problems why your heat pump water heater might not actually be working as well as it's supposed to. And it'll be nothing to do with the heat pump water heater that's outside your house, which will be do plus or minus 5% what the manufacturer says. The problem for this bit will be the rest of the circuit. So very much down to the install. Or heat pumps noisy? They shouldn't be. If they are, there's something wrong. A couple of things that make noise. This is off a compressor, and they're all going to be scroll rotary compressors on these systems. The compressor itself should be very quiet, and it'll have this around it, which is detritus off a tested system that I had knocking around, and that sits over your compressor sort of like that. This is dual purpose, and it kills a lot of the sound that comes out of it, which is, to be fair, very little anyway. And it also keeps some of the heat in, so the heat, which you're always going to have heat on one of these systems, it's parasitic loss, can't do anything about it, but you can minimise it by keeping this over it. So, why does your compressor make noise? Your compressor will make noise if it's not lubricated properly, because you've lost all the oil for some reason. The oil charge wasn't high enough when it came out of the factory, or it wasn't charged enough if it's one of the systems that a guy had to fill with oil. Probably didn't happen. Why else does your compressor make noise? Where, if you've got a heat pump water heater in the UK or Europe, it's probably not old enough to have had that. What affects oil return? System design, and if you've got it by a refrigeration system manufacturer who are going to be like Panasonic, Daikin, Mitsubishi, that's not going to be a problem. The problem you might have is if it's not installed level, because there will be gravity-fed oil return. And gravity-fed oil return. If you've got your house wall here, and the area where you've installed your heat pump is completely on the piss like that, well, if you've installed your heat pump, you can do it dead square to the ground. So that's a right angle, and you got your heat pump like that with its fans on it. If you do something like that, then the oil's going to drain that way, and it's not going to get back to the compressor wherever it is. So what you have to do then is to, in some way, whoever it is that installs it needs to put a platform up to make sure that it's square. And then this is based on the, or it doesn't need to be square so much as it needs to be plumb, which is probably not the right term for it because I don't know anything about that. But that means that it needs to be square, which is relative to a line that is, horizontal, shall we say, compared to the centre of mass of the system that you're considering. And the centre of mass that you're thinking of, which is centre of mass, not .com, this is actually the very centre of the Earth where gravity goes to. So when you're doing anything like that that's gravity fed, you need to absolutely make sure that it's plumb rather than square, and then you get oil back properly. Other option you might have for noise is, I don't even know why I'm bothering doing that, is fan noise. Well, that's a fan motor off one, which is, obviously, you can tell Japanese from the wiring colours. This is an ECM motor, so it's got AC that goes into it, gets turned into DC, by magic, and then it gets returned back into AC using a lot of electricery circuitry. And these are really, really quiet. These are so quiet that the only way that you know this fan is spinning is because you can feel the cold air coming off it if it's running. Otherwise, you can be stood next to it and you can't even hear it. So what happens, again, these aren't installed level. You can have the system like on the piss that way and it's completely fine because this rotation axis is going to be okay. So if you install the system at 45 degrees like that, well, this is still spinning in the same direction and the bearings inside will be fine. The problem comes if you install it either tilting back or tilting forward. When it runs, then you'll wear the bearing out, and then whenever the fan spins, it's noisy. Other thing is you might have crap, autumn detritus, lodged in your heat pump water heater if it hasn't been running all summer. All the leaves have come off the tree nearby and it gets sucked into it. So it could be mechanical obstruction like that. But if your heat pump is noisy and in any sort of noticeable capacity, and it's the sort of thing that your neighbour comes and complains about, there is something that's wrong with that system. Don't know what it is without looking at it, but something wrong because they should not be noisy, and in my experience, they aren't. Why does my heat pump keep freezing up? Well, you've got, when you're using this in winter, you've got T ambient, we'll call it, equal to, we'll use the rating point because we can, 7 degrees C. And that means that because this is just a heat pump running backwards, the temperature in the outdoor coil is, it's 7. They might hold it above 0 just to stop frost build up. They might not, depends on the manufacturer. So you end up with the evaporation T inside of, we'll just say very slightly greater than 0 degrees C, so you don't get frost, but it's enough that you get heat transfer from the outside into the refrigerant inside, which is what gives you the free heat from the outside, which you then pump into your house or you then pump into the water via the heat exchanger to then pump around your house. And what happens is this number here is your evaporation one is going to be below your dew point. Don't know what the dew point is exactly, but colder air holds less water. Dew point is going to be above the evaporation temperature. And what that means is that water vapor from the air will condense onto the coil. So you've got your cold surface here, which is one of the pipes of it, and that's going to be around 0 degrees C. The air coming over it is sort of 7 degrees C going that way. And the water vapor out of here condenses onto this surface here, which then drips off via gravity. Or if you're running below 0 here, so you've got let's just drop both temperatures for a laugh. And then you've got expert T ambient. Let's just say -5. -5 air over there, and then you've got this temperature here, which is -12, so we'll just use a 7K again. Well, this pipe is definitely going to be below the dew point at this point, over ice, not over water, as it would be above 0. But that means that any water vapour in the air that passes over it, of which there will be some, will be very, very, very happy to condense on this colder surface, because cold air doesn't even like holding very much cold water or water vapour. That condenses on here, and because it's below 0 degrees and it's 1 atmospheric pressure because it's outside in the atmosphere, what you'll end up with is a great big block of ice on your coil, and the system will at some point stop, and it might apply electric heat to it, or it might do an air cycle defrost. It might pump hot gas refrigerant through it from the compressor. Either way, something will happen when your system will stop heating water for however long it takes for it to defrost the block of ice that it now is. And then when it's done that, it will get back to heating your water. Do heat pumps work in cold weather? Yes, because freezers exist, right? You put your hand in the freezer, it's -20, your kitchen's at 20 degrees. Yes, they obviously work in low temperature, dependent on a lot of other caveats that we could be here for years. What happens as the outdoor temperature drops, the evaporation temperature of the refrigerant also drops. And that's because the evaporation temperature has to be below the outdoor temperature to be able to get heat flow into it. So it needs to be a couple of K at least below it. But you want it as high as possible for efficiency. So your outdoor T drops, your evap T drops. And as your evap T drops, your density drops of the refrigerant in the system. But your compressor or pump, compress or pump, is constant volume, approximately. Again, caveats, constant volume flow. So as density drops with constant volume flow, then accordingly your mass flow drops. And why does that matter? Well, the heat that you put into the water is equal to the power, again, there's a lot of caveats to this, is equal to the pump compressor power plus the heat that's absorbed by the refrigerant from the air. And this Q here is equal to P pump plus, and then Q is equal to delta H of the refrigerant, which if you look at my refrigerant video you'll find that everything that the fridge does, either absorbing heat through evaporation or rejecting heat through condensation, the vast majority of all the work done is latent heat, which is the delta H here. Delta H times mass flow. So this delta H is always going to be approximately constant, depending on the refrigerant, depending on the conditions. Yes, I know, don't at me. Relatively constant, that drops. So this quantity here that you absorb from the air, which is the free part of it, drops. But because the mass flow drops, your pump, not mass flow, density. Well, actually, it's because your pressure and density both drop with this. Yeah, that's kind of, again, whole of the topic. Pressure and density drop. The pump power draw also drops, but because you still want an indoor temperature of, say, 20 degrees, and the cooler the outdoor is, the bigger the delta T is across the wall, and it also means that the pressure ratio of the pump, as it gets colder, increases. And as the pressure ratio across the pump increases, the efficiency of the pump decreases. So now you're initially in a pincer movement, because the free stuff you get from the air goes down, the power you'll put into the pump, which is through your electricity meter, also goes down. But not only has it gone down, you've also lost in efficiency as well. So you actually put in, although you're putting in less power, it means you're getting less out of the air. So it's a bit of a double whammy. And then when you consider that because the temperature difference across the wall is greater, i.e. instead of it being, say, 20 in your house and 5 degrees outside with 15 delta T, well, if it's -5 outside, then you've got 25 delta T, and then you lose more and more heat through the walls of your house. So you're then asking the heat pump to put more and more heat in. And when you're asking it to put more heat in when it's running less efficiently because of reasons, and you're getting less free out of the air, you end up paying a lot more for it. So yes, it will work, but yes, you will see it in a massive reduction, depending on the design. Massive COP reductions. And I think this is kind of why people say that they don't work in cold weather. It's not that they, or really cold weather, it's not that they don't work, it's just that they become less efficient. The get out of jail free card for heat pump water heaters in this scenario, of course, is that you should really size them with a bit of overhead on the coldest day of the year that you'll ever experience, so that when this happens, you've still got enough heat capacity to achieve the heating you need inside and be able to deal with the colder outside temperature, i.e. more mass flow that you need, or not less mass flow, for reasons. You need the pump to be able to be big enough to be able to do that, to get the capacity, and the evaporator has to be able to be big enough to get enough air over it to take in, or to get more air over it to make up for the mass flow drop as the pumping drops, as the pressure of the refrigerant drops. But what that means is then for the rest of the year, you're then using a heat pump that is probably considerably oversized if you're in the UK, when we might get below -5 once, and the rest of the time we're around 5 to 15 degrees is probably fair in the UK. So that means the one day that you actually really, really want your heat pump, the chances are, because the salesman didn't want to give you a massive price and you didn't want a great big unit in your back garden, you've got a slightly undersized heat pump, and then it becomes horribly inefficient and doesn't work on the coldest day of the year. So pick your poison. You can have a more efficient system for the majority of the year, or you can have one that will actually do what you want it to do on the one coldest day of the year. But otherwise, just put a coat on indoors, because you'll have to. Obviously, it's up to you if you want to get one, or if you've already got one, I guess you're stuck with it. But, work out from the price alone, the acquisition cost or the capital upfront cost of this is probably means you're never going to break even though a heat pump will last probably as a fridge 20 years, whereas your gas boiler, you'll be lucky if you get 10 out of a new one. If you're really lucky, you've still got one of the old 70s ones. They might not be as efficient, but they don't go wrong. So, obvious questions. Do you need bigger radiators? Maybe. Are they noisy? No, not if they're installed properly, and if they are noisy, it's because there's a problem with it. Why does it freeze up? Well, it freezes up in cold weather because that's just how fridges work. And it's called a defrost on any other fridge. It's called a defrost on this as well, but it's something that you're equally familiar with from your fridge freeze or whatever. So it is normal, unless you've got low refrigerant gas, but that's a whole new problem, and then you won't get any heat, so you'll know there's a problem with it. And do they work in cold weather? Yes, they do work in cold weather, but they're not as efficient as they would otherwise be. Before anyone asks me, I think they're great, they're really good. Would I buy one for my own house? No, I wouldn't. That's all she wrote.